Welcome back to Chem 4300. In this video, we're going to continue Chapter 10 on wave-particle duality. Now, at the beginning of the chapter, we learned how ideas about light being a wave were being challenged by experimental evidence, such as blackbody radiation and the photoelectric effect. And this led people like Planck to propose that somehow energy was being quantized. And it led Albert Einstein to propose that light maybe is not a wave, but actually is a particle that somehow has wave-like properties associated with it. So Einstein suggested that the energy of this particle was linearly proportional to its frequency, and that the proportionality constant was the Planck constant. Now, to make sense of the wave-like behavior, what Einstein proposed was that the light wave intensity, or the square of the wave amplitude, can be interpreted as a probability, the probability that the photon is being absorbed or emitted. This is a pretty radical idea. The idea that light is a particle and that its wave-like behavior, the wave function, is actually only telling us what the probability of finding that particle is. So let's just hold on to that idea for now, and let's switch from looking at what was known about light at the time to look at what people were trying to learn about the structure of matter at the atomic level. So at the same period, people were trying to understand what were the constituents of the atom, and based on those constituents, can we explain, say, the light absorption and emission spectra of atoms? So let's take a look at the data leading up to this period in time. So in 1814, Fraunhofer, as we know, measured the spectrum of the sun, and in that process he saw these dark lines, and some of those lines he associated with the sodium flame emission spectra. Later, Kirchhoff and Bunsen found that they can actually assign the rest of those lines in the sun spectrum to the emission spectrum of other elements in their flame spectra. So that was actually very important for them to try to take these emission lines to determine the composition of the sun and other stars. In 1885, Balmer and Rydberg found that they could look at the hydrogen emission spectrum and predict the positions of these lines with a very simple formula. They found that 1 over lambda was equal to some constant, which we now call the Rydberg constant, times 1 over 2 squared, the integer 2 squared, minus 1 over the integers 3, 4, and 5, and so on, squared. This simple formula predicts all of the hydrogen emission lines. Now, why it works, they didn't know, but they did find that there is some simple formula that must be some clue as to the structure of the hydrogen atom. In 1896, Siemens saw also some interesting things, that if he took a sodium flame and he put it in a magnetic field, the sum of those lines would start to broaden. And this told us that whatever is inside this atom, it somehow has to be interacting with magnetic fields in order to cause this kind of effect. Now, in 1897, Thomson discovers the electron and is able to measure its mass to charge ratio. Now, Thomson knew that electrons were constituents of atoms, and he knew that atoms were neutral, and they had diameters about 1 angstrom, 10 to the minus 10 meters. So he proposed a structure that had a neutral atom, which was composed of a positively charged cloud, so a 1 angstrom, imagine a 1 angstrom positively charged cloud, with these small electrons fixed inside this positively charged cloud, like, say, plums in a pudding. So the pudding is the positive cloud, and the plums are the electrons, and they were fixed, they weren't moving, and they were just distributed somehow inside this cloud of positive charge. Now, this might seem like a sort of a silly model given what we know about the atomic structure now, but at the time, actually, it was a reasonable model based on what he understood about electromagnetic waves being generated by moving charges and things like that. He knew that the atom didn't just spontaneously radiate away all of its energy. So he proposed this model, and it actually was fairly sensible given what we knew at the time. Now, in 1895, Roentgen discovers X-rays by firing electron beams onto a metal anode, and in 1896, Becquerel discovers radioactivity in uranium minerals, and looking at these radioactive minerals Rutherford looks at gas ionization and using these minerals, and finds that there are two types of radiation coming off of these decaying uranium materials, which is alpha and beta rays. That these alpha rays, later he will discover, are just positively charged helium nuclei, and the beta rays turned out to be electrons and positrons. Now, Rutherford was actually a student of Thomson, and he knew that he was able to produce these alpha particles, a beam of alpha particles coming off of these radioactive uranium atoms. So he decided to test his mentor, Thomson, plum pudding model for the atom. And so he fired these positively charged helium atoms, or what he knew was just alpha particles, at metal foils, and he expected these positively charged particles to fly into this Thomson model of the atom and just be sort of slightly deflected on and off, different directions as it sort of came close to each one of these atoms. But what he found, in fact, actually, is that most of these alpha particles went right through the foil and didn't collide with anything at all, except a few that came bouncing almost directly back at the gun that was sort of the uranium that was generating the positively charged alpha particles. And that he found was pretty odd. Somehow it meant that whatever was causing the repulsion of the alpha particle was concentrated into a very small area. So whatever this positive charge that was compensating the charge of the electrons, what he thought was a cloud that Thomson proposed, couldn't be a cloud because what was happening is that those alpha particles were bouncing right back at them. The only thing that could do that was if all that positive charge of the atom was concentrated into a very small region, and when by chance this alpha particle hit it, then it would bounce almost directly back. Otherwise, if it was a cloud, the alpha particles would have gone, they would have passed through the cloud and just deviated maybe ever so slightly. They wouldn't have come firing back at him come bouncing back at him as he fired the alpha particles at them. So on the basis of this result, he concluded that all that positive charge, which is most of the mass of the atom, was concentrated in the center, and that these electrons, which are very light, somehow must orbit this positively charged nucleus like the Earth around the sun. But of course, that was a bit of a problem because he knew Maxwell's equations told him that any accelerating charge, like an electron moving around in an orbit around a positively charged nucleus, would radiate light waves and lose energy. So these orbiting electrons wouldn't be stable in their orbits, and they would just spiral down into this positively charged nucleus, and it wouldn't work. You wouldn't be able to have this 1 angstrom diameter neutral atom, because it would just always collapse and radiate all of its light. So he knew that his model was not sensible based on Maxwell's equations, but he knew that Thomson's model wasn't sensible either based on the alpha particles recoiling back directly at him as he fires them at these metal foils. So that means that somehow we have to have some kind of picture of the atom that's consistent with this, but not lose energy as these electrons orbit around. So this was puzzling. So in 1913, Niels Bohr proposed an atomic model where the electron orbits the nucleus, just like Rutherford proposed, but the electron is not allowed in this model to radiate light while it's in an orbit. So Bohr gives no reason why this doesn't happen. Doesn't bother to explain it, intentionally doesn't bother to explain it. He just says this is what happens. And an electron then will gain or lose energy by jumping between orbitals, and that's when the atom will emit or absorb light. And the frequency of the light that is emitted or absorbed is just the difference in energies between those orbits. So based on these three assumptions, he puts together a model for predicting the wavelength of the light that's given off by the hydrogen atom, and he predicts this equation here. So he predicts that 1 over lambda is equal, well, here's just constants, that's the electric constant, here's the mass of the electron, here's the fundamental charge, these are other constants here, this is the charge of the nucleus, so for hydrogen that would just be 1, and then he finds this 1 over n final squared minus 1 over n initial squared, where these are integers, and these are associated with the different orbits. And this looks exactly like the Rydberg constant, and in fact, this part right here gave perfect agreement with the Rydberg constant. So this was, even though he couldn't explain why the electron doesn't radiate light, why it's in orbit, he was able to come up with an equation that gave him the Rydberg constant. So he knew he had something that was right in his thinking about this. He didn't understand part of it, but he got an answer that was in agreement with the experiment. Okay. So unfortunately, this model works for hydrogen, but it doesn't work for multi-electron atoms. So it was useful in trying to understand some of the structure of the atom, but in the end, it turned out that it wasn't going to work for more sophisticated problems like multi-electron atoms or molecules. So now we come to the next part of the story, which is Paris in the 1920s. So we have all of this worked out now before this about the Bohr's theory and the structure of the atom as we learned it from Thomson and from Rutherford. And now we come to how we're going to fix this problem that we don't understand why atoms don't radiate away all of their energy as electrons orbit. So we come to Louis de Broglie, who worked out this hypothesis. He said, if light, which everyone thought was a wave, could be like a particle, then particles, like electrons, nuclei, and the atoms, might also behave like waves. Okay, it sounds very simple, but he actually worked through the consequences of this. So what de Broglie imagined was that we can describe particles as wave packets. And what we know in this class about wave packets is that the particle's velocity, and this is what de Broglie said, the particle's velocity can be equated to the wave packet's group velocity. So we know what a group velocity is. This is the derivative of the dispersion relationship with respect to wave number. And so de Broglie said, take the wave velocity, the group velocity, and set it equal to the particle velocity. So this is a wave property being set equal to a particle property. That's what de Broglie suggested. And then from Einstein's relationship, so if we say E is equal to h bar omega, or rearranging it like this, he can get that the dispersion relationship. He can say that the derivative of omega with respect to k has to be the derivative of E with respect to k. So okay, so hold on to that thought. So to get dE dk, he just writes down the energy of a particle that has only kinetic energy, which is p squared over 2m, and he writes dE dk is p over m dp dk. So now we've turned the problem into finding that partial derivative. And so we take this result that the group velocity, which is related to the derivative of the dispersion equation, through these relationships here equal to this, we now get an expression where we now have momentum on both sides of the equation. So we have our wave part over here and our particle part on this side. So if you look at this, you can rearrange this and you can get that dp dk is just equal to h bar. You see here's p over m cancel, so that's just equal to h bar. So if you integrate this expression, you get that p is equal to h bar times k, or p is equal to h over the wavelength for this matter wave. Now, this is the same result that Einstein found for the photon, that the momentum of the photon was h bar times the wave number. But de Broglie takes this approach and he comes up with the same result by assuming that particles like electrons, protons, or atoms can also be described as waves, and he gets the same relationship between the particle property and the wave property, momentum and wavelength. So this is how he describes his matter wave of a free particle. And in this derivation, notice that we found a dispersion relationship that we can rewrite in like this. And we'll come back to that later. Now, at the time, it was well known that X-rays will give you a diffraction pattern. Remember, X-rays now have been discovered. So if if matter is actually behaving like a wave, it should diffract like some electromagnetic wave would diffract. So if de Broglie took an electron, which is a particle, with this velocity and calculated its wavelength, it actually turned out to be on the order of 0.122 nanometers, which is very similar to what was known to be wavelengths of X-rays. So if they can see diffraction of X-rays, they should be able to see diffraction of electrons. And in fact, they could see this. So let's take a look then. So these matter waves, which are composed of electrons, have the same wavelength as X-rays, which is just electromagnetic waves. So in 1927, Davison and Germer did an experiment where they fired electrons at a piece of crystalline nickel. So nickel is a lattice of nickel atoms, so it forms a diffraction grating, and so it forms a regularly spaced lattice, so that when you fire electrons at this, you can get them bouncing back into some detector as a function of angle. Now at the time, people were already using X-rays and firing X-rays at crystals and getting nice sharp diffraction patterns that was related to the positions of all these atoms. So when Davison and Germer fired an electron beam, they calculated using de Broglie's relationship what the wavelength electron beam was, and they found that the electron beam scattered with a interference pattern that was consistent with the wavelength predicted by de Broglie. And so this is an example, something we now call low energy electron diffraction, where this is an electron gun fired down, in this case, onto the surface of a silicon 100 surface. And you can see when the electrons bounce back, because this surface then has this periodic spacing of silicon atoms, we get this constructive and destructive interference pattern. And this pattern then is exactly what you would predict by calculating the electron's wavelength and using the spacing of the silicon atoms to get the diffraction spots there. So this proves that electrons, this is not X-rays, these are electrons being fired at the surface, will actually diffract as with their wave-like properties predicted from de Broglie's equation. So in 1927 then, we've established that both light and matter can be observed as a particle or as a wave. So this is what we call the wave-particle duality. And this behavior is only observed at the subatomic scale, so where the masses are small enough to get wavelengths that are, masses are small to get large enough wavelengths to see these wave-like properties. So just to get you calibrated on this, let's take a 16-pound bowling ball, a macroscopic object, and let's calculate its wavelength. Say it's moving down an alley, a bowling alley, at 20 miles per hour. Okay, that's a reasonable speed for a bowling ball. If we take de Broglie's relationship here, which is lambda is equal to h over the momentum, we write momentum as m times v. We can plug in all of these values here, 16 pounds times 20 miles per hour, and we'll get a wavelength of 10 to the minus 36 meters. Now that's pretty small. So let's take that idea and continue with it. Let's say that if we had this 16-pound bowling ball and we wanted to diffract it, so we know that a wave moving through a small slit will diffract as it moves through the slit if the wavelength is on the order of the bowling ball. But what we're going to do is we're going to try to slow down the bowling ball to the point where it has a wavelength on the order of a doorway. Right? So we know if we get the wavelength to the slit width, we'll get diffraction. So we're going to throw a bowling ball, but we're going to throw it so slowly that its wavelength matches the doorway width so that we can diffract the bowling ball. All right, this sounds crazy, but let's see what we would need. So we're going to do the diffraction. We're going to have a lambda of 3 feet in order to get diffraction. So we know that to get that wavelength, we need h over 16 pounds divided by 3 foot lambda. That gives us a speed of 4 times 10 to the minus 33 inches per second. All right. that is unbelievably slow. To move 1 inch at this speed would take 10 to the 24 years. That's bigger than the age of the universe. So practically speaking, even though the bowling ball does indeed have a wavelength when it's moving at some finite speed, for you to observe these wave-like properties would be virtually impossible. All right. So this wave-like property is only observed at the atomic scale when you have, or smaller, when you have these small masses. Okay. So generally speaking then, we only observe wave properties or particle properties depending on how you're doing the measurement. So which measurement you do, we'll see that you'll either observe it as the particle as a particle, or you'll observe the wave-like properties of that particle. So let's take a look at dispersion. We know that a free electron, say, is confined to some space that's on the order of an angstrom here. This is 10 to the minus 8 centimeters. We want to know how long it will take for that wave packet to spread to twice its original width. Now, we worked this out in the chapter on waves. We saw that if you had a Gaussian wave packet, it will disperse in time with this equation here. And so what we needed was this alpha term, which is the second derivative of the dispersion relationship. But for a free electron, we know that the dispersion relationship. We saw this from de Broglie's derivation. So if we take this guy, we take the second derivative with respect to k, we'll get h bar over m. And plugging this alpha into this expression up here, then we get this equation. And now let's continue to see how we solve this problem. So what we're going to do is take that equation, we're going to rearrange it in terms of the time it takes, and then we're going to define the ratio of delta x over the initial delta x as some variable s, and we're going to rewrite this expression like this, and then here. So now it's written in terms of the time it takes for it to expand by some factor s is given here. And so we want to know how long it takes for the packet to go to twice its original width. So that means s equals 2. So we plug that into our equation here and here. S 2 squared is 4 minus 1 is square root of 3 here. And that gives us a value of 0.15 femtoseconds. So it doesn't take long for an electron that was confined to a 1 angstrom region, a wave packet, to spread out to 2 angstroms. As you can see here, only 0.15 femtoseconds. Well, let's put this on a little more physical scale for us. Let's say we have the same electron confined to that 1 angstrom, but now we want to know how long it takes to exceed the width of the solar system. So it starts out at 1 angstrom, and how long does it take for that to disperse out to the width of the solar system? Well, take the distance from the Sun to the Neptune as, say, as 30 astronomical units here, so that's given by this value in kilometers. So if we want to calculate the ratio, starting at 1 angstrom and putting in the 60 up here, for so that's the distance. So twice that is the diameter, and so we get a value of s of 8.98 times 10 to the 22. So let's go back to our original equation. We'll plug in that value for s, and we get a value of 3 months. So an electron, which is a wave packet in this de Broglie picture, will start out in 1 angstrom, and with that dispersion relationship, will spread out in 3 months from 1 angstrom to the size of the solar system. Now, 3 months seems like a long time, but keep in mind, Voyager 1 left Earth in 1979 and didn't reach the end of the solar system until 35 years later. So 3 months is actually pretty fast in terms of that time for the electron to disperse. So next we come to this idea that we saw in the wave chapter of wave packets following an uncertainty principle. We knew that we couldn't specify the position of a wave packet without losing information about the wave numbers that went into it. So if we wanted to know the wave number precisely, then we couldn't know where that wave was, because if it was very narrow wave numbers, then it had a very wide range of position. Likewise, if we put it into a very small region of x, then we needed a lot of wave numbers to make it localized into that position of x, so we lost information about what the wave number would be. So that was the uncertainty principle with waves. So we can now use this in quantum mechanics, and this brings us to what's called the Heisenberg uncertainty principle. So we know that our electron or our bowling ball is confined to some region of space, and we know that there's a wave associated with it, this wave. And so let's say we have a Gaussian wave packet, and we know that the product of position and wave number have to follow this relationship from the wave chapter. But now with de Broglie's wave, we use the relationship between momentum and wave number. So momentum is just Planck's constant divided by 2 pi, or h bar times k. So we can now substitute in for delta k becomes delta p, and we find that the uncertainty principle that we saw in the wave motion chapter becomes, for the matter waves, delta x delta p is equal to h bar over 2 for a Gaussian matter wave packet. So this Gaussian matter wave packet, remember, Gaussian wave packets have the smallest uncertainty product. So generally speaking, for any arbitrary shaped wave packet, then we know this is true, that delta x delta p is greater than or equal to h bar over 2. This is called the Heisenberg uncertainty principle. This was Heisenberg worked out, based on this understanding of de Broglie's matter waves, this principle, and you can see actually a similar relationship with time and frequency, which we also saw that with energy and time. So from wave theory, we saw this. If we use Einstein's light quantum hypothesis, we can turn this guy into this uncertainty principle, that delta E delta T has got to be greater than h bar over 2. So these are the uncertainty relationships that we'll see in quantum mechanics. And there'll be other types of uncertainty relationships we'll get to, but these are the ones that you can see most obviously based on our understanding of wave motion. So that's it for this video. In the next video, we're going to look at how we're going to get a wave equation for de Broglie's waves. And that's where we come into the work of Erwin Schrödinger, who said, how can I take de Broglie's idea of a matter wave and come up with a wave equation? And we'll look at that next.